Recall last time in class, we left the class with a definition of this object right here. What the heck does this mean? At least a temporary definition. In the last video, we developed an idea for what this R sub n is. It's a sum of right-hand rectangles. We partition some sort of interval into subintervals of this length, and we make a whole bunch of rectangles of this length, and we sum the areas of all the rectangles so that we can approximate the area under the curve here. This thing right here is indeed, it represents the area under the curve of f of x from A to B. Turns out this is a signed area, signed, which means that it can pick up negative area because f itself in this sum could be negative. And of course, there's no absolute value anywhere here. And therefore, it's possible, on this definition of area, our new definition of area, it's possible to have negative area. Notice that Greeks honestly didn't even give a good satisfactory definition of area. They only gave intuitive definition of area. They sort of called it a primitive notion, what this understanding of area is. All of a sudden, after today's video, we are going to have a first official, concise definition of area, and we use this thing called an integral to describe area. Let me just write down how you would write this, or how you would read this. This would be the integral. You would read that as, so this object, as the integral of f from A to B. All right. And here's how we think about it. The area under the curve. Area is huge. So as emphasized in class, in Math 1A, we emphasized to death that the derivative is nothing more than a slope. In this class, Math 1B, we emphasize to death that this sign, when we see something that looks like that, that's nothing more than an area. So, as I said, this is a provisional definition. I don't think it's satisfactory because we could accidentally, with this limit, receive some sort of constant or finite answer when the area itself is actually infinite. Like, for instance, what if the right-hand rule happens to work where some other rule, like the trapezoidal rule or the left-hand rule, diverges to infinity? So I don't think this is a satisfactory answer quite yet. We want to come up with something a little bit more general and a little bit more, I guess we just need some sort of definition that accounts for those stray cases. And in order to do that, here's what we are going to do. This is going to be like a recall back to sort of the epsilon delta definition of a limit. After all, this will be, the definition of the integral is a limit, just like the definition of a derivative is a limit. But let's think of a good way to define this. I want to be able to say, if I really want this function here maybe to be integrable, so here's my f of x, and now here's x-axis, y-axis, and let me give some sort of partition right here, A to B. If I want this to be integrable, the same process that Weierstrass and Cauchy came up with is we're going to employ this and say, let's say somebody gives us a very small number. So someone gives us a small number. Small positive number. We call this number epsilon, bigger than 0. Imagine that to be very small. Our question would be, if we wanted to find area, so by the way, this area, let me kind of draw this area. So we want to officially define the integral. So we want a way to express this area perfectly. Okay. So someone gives us a very small positive number, epsilon, and we want to ask, does there exist, does there exist some small corresponding number, delta bigger than 0, such that if we make a partition, any partition, for which each of its subintervals have length less than delta, then delta. If we make, okay, so does there exist some sort of response, just like in epsilon delta definition of a limit? So somebody challenges us with a very, very small number. Can we make a partition small enough whose subinterval lengths are small enough? So like, I'll also define what a partition here is in a second. So the subinterval lengths are small enough such that if we make any partition for which each of its subinterval lengths have length less than delta, then the sum, I would say this, then the sum of the areas made by the rectangles differs from the area A. Oh wait, let me make sure I'm making a complete sentence here. Does there exist some delta bigger than 0 such that if we make any partition for which each of its, yeah, this is good, then the sum of the areas made by the rectangles differs from the area by less than epsilon? If so, then the function is integrable. Then this exists, the integral from f of x dx, the integral from a to b of f of x dx exists, and it equals epsilon, or it equals a, which is this area right here. Okay, so that was a whole bunch of hoopla, but that is like the core idea. Whoa, that's cool. A, this area. So here's what I'm saying. Somebody gives us, oh man, it looks like it's like kind of coming out at you. That's cool. Somebody gives us a very, very small number. And we want to say, okay, so is there some sort of corresponding small number delta so that if I cut up this interval from A to B in such a way that each of the pieces vary by less than delta, then the rectangles made, so here, I can draw this. So here's one maybe, here's another, here's some sort of random partition. Here's my rectangles. Oh, another really important thing. Another important thing is the height of the rectangle can't matter. Like, for instance, there's these special points. Okay, so that would be what I call a tag. So this one looks to be like on the first side here. A seems to be a tag. A tag in each of the subintervals is simply some place where you take the rectangle's height. Okay? So these are all tags. For instance, maybe in this picture, this would be x sub 1, because A is x sub 0. This would be x sub 2, this would be x sub 3, and this would continue. Let me do a few more. So we take some random tag, and I'll explain what the actual integrability part means. So this would be x sub 4, x sub 5, and this continues till at some point we have this rectangle and this rectangle. This is far more general than the other one, and I'll do one more. So let's draw the tags. This would be a tag. Some random point in this last interval. Here's another one maybe. Here's another one. Okay, so general idea. Let me talk generally. Last tag. So this would be, A would also equal T sub 1. This guy right here would be T sub 2. So that's simply saying that is the tag for the second interval. This right here would be my second interval, second partition subinterval, and this would be the tag for the second partition subinterval. This right here would be the tag for the third subinterval. 1, 2, 3. T sub 3. And of course, this is T sub 4 right here, T sub 5. And they're just arbitrary points inside of the interval. If we can find some sort of partition, somebody gave me a very, very small number, right? If we can find some sort of partition such that this overlap area, or I guess the missed area, such that all of this, and this is loose, this is not a perfect representation for what the integral really means. So all of this is pretty much the area where we are not perfectly approximating, either an over approximation or an under approximation. If we can force all of that spare area to be less than any number we choose, okay, this is huge. I finally got the picture ready. So, if we can force this yellow spare missed area, right, along the top right here, and this continues, this is a dot, dot, dot. We want to imagine rectangles all the way across. Oh, let me finish this down here. Gosh, I'm all over the place. X sub n. This would be x sub n. This would be x sub n minus 1. This would be x sub n minus 2. X sub n minus 3, and of course this would be the T sub n minus 2. This would be the tag where we choose the height of the rectangle, T sub n minus 1, and of course right here, T sub n, that would just be T sub n. Okay, so if we're handed a tiny number, 1 over a billion, if we can choose a small enough partition, if we can dice up this interval finely enough, into enough subintervals. Really what we want to say is there some sort of corresponding small number such that if we force any partition to have each of these lengths smaller than that response number, these lengths, then the sum of the rectangles made, the sum of the area of the rectangles made, will differ by the actual area by less than epsilon. Oh, I'm using the big words now, I guess. Then we can say that the integral exists. So to put it all in crazy words, and also let me officially define what a partition is. A partition of an interval A to B is a set of n increasing numbers from that set A to B, in particular where the first one in the list is A and the last one in the list is B. So for instance, for example, a partition could be this set, A, which is equal to x sub naught, comma. Oh, I guess it would be n plus 1, increasing numbers. X sub 1, x sub 2, x sub 3, and this would continue until we get to x sub n, which is the same thing as B. So I'm just taking n plus 1 numbers, one of them being A, one of them being B, from this interval. And also notice this, x sub z, or excuse me, where x sub 0 is less than x sub 1, which is less than x sub 2, all the way up to x sub n. So they're increasing in number. Think about it literally as a partition, though. We're just cutting up the interval. That's all it is. And naming those cuts by x here. And a tag is a number I guess I said where the rectangle's height is taken, or I should say this, the nth tag, the kth tag is a number in the kth interval. In other words, t sub k exists in the interval, and this is all going to be made more official here in a second. This would be x sub k minus 1 to x sub k. And that's in the picture, right? So t is just one of these green numbers that exists in the second interval. T sub 2 is just some number in the second interval. And this is simply where it's an arbitrary number where we take our rectangle's height. So for instance, the right-hand rule uses the right endpoint as the tag. Okay, so we need to be able to find, somebody hands us a small number. We need to be able to find a maximum width of a partition. Is there some corresponding minimum number or small number? Somebody hands us a tiny number, epsilon. Does there exist some delta bigger than 0 such that if we shrink our partition lengths to be less than that delta, then the area made by the rectangles summed up differs by the actual area by less than epsilon? If we can say yes, then we know that the integral exists. Okay, so heavy math here. We won't go too in depth in the official definition, but here's what the actual definition looks like. We say that a function f is integrable over A to B. Implicitly here, A is less than B. If there is some A in the reals, so this is kind of like our limit. This is the same as the capital L in our limit definition, such that the following holds. So here's this A, by the way, is the area. So we want to think about that as area, such that the following holds for each small number, epsilon bigger than 0, there is some corresponding small number, delta bigger than 0, such that for each partition P, which is equal to, A, which is x naught to x1 to x2, comma, dot, 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 comma, x sub n minus 1, x sub n. For each partition like this, such that the norm of the partition. Okay, so what the heck does this mean? That simply means the length of the greatest subinterval for each partition such that the norm of the partition is less than delta, and for any choice of tag, T sub k, where T sub k, of course, is an element of the kth interval, x sub k minus 1 to x sub k, then oh yeah, perfect. The difference, the absolute value of the difference of the sum as k ranges from 1 to n, so we're going along our intervals, each of these intervals, of f evaluated at our tag times the length of the kth interval differs from A by less than epsilon. Let me make sure all my English is okay. For each epsilon greater than 0, there is some delta bigger than 0, such that for each partition, such that the norm of the partition is less than delta, and for any choice of tags, partition of AB, and for any choice of tags, T sub k, where T sub k is an element of the kth interval, then this sum of rectangles differs from the area by less than epsilon. So here, I'll do this. It says the rectangles' area differs from actual area by very little. Indeed, arbitrarily little. Okay, So if we can always find a partition small enough, whose subintervals are small enough so that the sum of the rectangles differs by the actual area by very, very little, then we can say that the function is integrable. If this is the case, then the function is integrable, and that number a is denoted, it is denoted by the integral from a to b, like I said, this is how we would read this, of f of x dx. And last thing I'll say, to make this easier, perhaps this is easier. Indeed, if a function is integrable, then we can use this old definition we had last time. Then one of the valid ways to express that integral would be the integral from a to b of f of x dx is indeed equal to the limit of the right-hand rectangles as n approaches zero, or excuse me, as n approaches infinity of r sub n. If a function happens to be integrable, then we can go back to this definition. So that is the official definition. I'm going to rewrite it, or I'll show you from our results of calculus worksheet what it really means, or I'll just emphasize it in the official language. Let's see if I even got it right. Yep. Okay. Saying the same stuff. So what I just tried to parse here was this official definition, and it's a little bit weird to take in, and it's not super crucial that we fully understand that to be successful in this class. But if you want to have a deep, real understanding of calculus and the integral, think about why this works. Like I said, essentially what we were saying is you can cut up the interval from a to b finely enough so that the resulting rectangle's area differs by the actual area by as little as you choose. Then you can say the function is integrable. So again, let f of x be a function defined over a closed interval a to b. We say that a number a is the definite integral of f over a to b, over the interval a to b, and that a is the limit of the Riemann sum. So this is what I call a Riemann sum. This object here, any sum of this form is called a Riemann sum. If the following condition is satisfied, for each epsilon greater than 0, there is some delta bigger than 0, such that for each partition, I think I nailed it, partition P, which equals this thing, by the way, x sub 0 is equal to a, I should have that in here, and x sub n is equal to b, of a to b, with the partition norm, and again, that's the length of the largest interval, less than delta, in any choice of tag, and again, this is simply the point where we take the height of the rectangle in each of those intervals, we have that the difference of the sum of all those rectangles' area from the actual area, or this random number, is less than epsilon. Then what we say, actually, this is how we find the actual area. So I'm a little bit abusive here. We choose this number to be the area under the curve if this is the case. So that was a little bit backwards, but essentially we're getting the right idea. In particular, if f is integrable, then we can use the right-hand rule. This is simply the right-hand rule right here, all drawn out. Super, super nice. We are going to use this. It's a lot more easy, or I would say it's easier to get kind of a grasp on this definition than this epsilon delta definition, although this is the official definition of what it means to be integrable. This is known as the right-hand rule. Based on this definition, each of the following integration laws can and should be proven. All right, let's see what we got. All right, this one's huge. It is famously hard to prove, though. If we have a continuous function over a closed interval, then guaranteed an integral exists. In other words, if I have a continuous function, then finding the area is certainly possible. Finding the area under the curve is certainly possible. In, I think, your guys' quiz 3, your extra credit guides you through how to prove this. Okay, it's quite heavy. A lot of, you have to go based on this fancy definition in order to prove something like this. Whereas a lot of these other guys, we don't necessarily need to. All right, let's prove some of these guys. So let's kind of get an intuition for what these guys say, actually. Okay, so this one says that the integral from a to b is equal to the integral from a to b of f of x. By the way, we are supposing that these are both integrable. So in other words, we know that we can find the area. And we know what this means is we know we can use the right-hand rule if we so choose, because we are supposing that they are integrable. What this says is the integral from b to a is equal to the negative of the integral from a to b. It's kind of like we're taking areas backwards. That's what we're doing. In a similar way, where if a is less than b, that implies that b minus a is bigger than 0, which means that 0 is less than negative a minus b. Those are indeed the same object. So those objects, in order to treat b minus a and have that kind of like swapping action, I think we actually proved this one in today's video, so we'll see how it works. You're reading from the larger one to the smaller one, which means we're going to pick up negatives if you start with the smaller one and you go to the larger one as we're gliding over the intervals. But anyways, we'll see why that one is true. This first one is a little bit unintuitive. Really, what we have this rule for is so that this rule right here, IL5, which is going to be the bane of our existence, at least its proof is. Honestly, it's kind of intuitively true. As we look at it, you'll see why it's intuitively true. So the point of this, the invention of this, is so that this will hold for all A, B, and C. All right, IL2, what does this say? Okay, so check this out. If we take an area of a function from A to A, what that means is we didn't actually move at all. So this would kind of like be the area of a vertical line, or a vertical line segment, if you will. That's a little bit abusive. But of course, a line segment has no area. A line segment has area of 0. Indeed, what this is kind of saying, to kind of draw it, what is the area under a point? Like, how would that make any sense? How would you say, here's A down here, but what would you say the area of this line is? It has no width or anything like that. It only has a height. So it's what you would say one-dimensional. There's no area in one dimension. So that's why we say that area is 0. So if you have the lower bound equaling the upper bound, then you know the area is 0. Okay, what this guy says, if we take the integral of some number times the function, then we can take that number out. That number can exit this integral sign. And this is quite easy to prove. After all, this is defined as the limit of a sum, okay? The limit of a finite sum. You can certainly undistribute a number from a finite sum, and you could also take a number outside of a limit. That's really what we're using right here. We're using a limit law and the distributive property. It's a combination of both of those that we use in order to prove this. Quite easy to prove. All right, let's look at what we say. So for IL4, it looks like this integral sign can distribute over addition, all right? So we can scoot this integral sign first in front of F and then in front of G to create the sum of two integrals. So this says the integral of a sum is the sum of integrals. That's what this says. The integral of a sum is the sum of integrals. I think we will prove this one. Again, if we use the right-hand rule, we know the limit of a sum is the sum of limits, and this object right here is defined as a limit. Look, this thing right here is a limit, and since we know the limit of a sum is the sum of limits, this should be true. Also, we have this sum we will have to deal with, this capital sigma. And that, in order to distribute sort of a capital sigma, that's really a result of the associative property and the commutative property. All right, let's see what else we got. This one's huge. I like this one because it is certainly intuitively true. If I draw a picture, something like this, I have some sort of function like this, and maybe I have A right here, B right here, and C right here. This right here, this blue area would be this object right here. The area under the curve from A to B, right? This area right here would be the area under the curve from B to C. All right? So, again, this blue area right here is the area under the curve from A to B. This red area right here is the area under the curve from B to C. Oh, wait. If I add those two up by the area addition postulate, honestly, it's kind of like a direct result from the area addition postulate. That is going to equal this green area, which would be the area all the way across. The integral from A to C. So it's certainly very intuitively true. What gets tricky is when we expand that to arbitrary A, B, and C. Notice I implicitly assumed B was between A and C. But with this granted and with this granted, we can use arbitrary B and C. In fact, typically these are definitions. Because there is actually, so far, no way to define this object, or excuse me, this object. There's no definition because it's implicit that A is less than B. So we don't even know how to define this. But I'll cheat and do a kind of like a faux proof of this to at least be a little bit convincing. Okay, how about IL6 here? Let's see what that says. IL6, this one right here. This one, again, is quite intuitive. You just have to draw it out. So say I have some sort of function. It goes like this, maybe. Here is the maximum height. That would be max F. And here's the minimum height, min F. That's what these objects are. Here's max F, min F. And let's do, I don't know, some arbitrary interval. Let's go from A to B here. This thing in blue is the integral itself. That is the integral. But that blue area is certainly more than this green area. But what is that green area? Well, it's this length, which would be B minus A. That length is B minus A. Times the height, which is min F. So that would be the area of a rectangle, ladies and gents. And we've proven the area of a rectangle. That is base times height. So this green area would be B minus A times the minimum of F. But that's certainly less than the blue area, right? But that blue area is certainly less than, I'll use red, this red area. Okay, so that's maximum F. Okay, I won't fill it out too much. So that would be less than max F times B minus A. Times B minus A. Okay, bad board management, but you can kind of see IL6 in the picture right there. Something like that. All right, this one's also pretty intuitive. If f of x is less than g of x, then the sum under, or the area under their curves are going to respectively be less than each other. So I'll draw this guy. We have a to b. Maybe some f of x like that, g of x like this. So hopefully it's obvious that that green area is certainly much larger than the blue area. Okay, that's what this IL7 says. IL7. All right, there you go. So nice picture with all the colors and everything. That's what all these say. We want to use these a lot, and we'll get practice with these. But first, I wanted to show you a proof of some of them. We'll hopefully get to a point as a class where all of these are proven amongst our next few quizzes. But let's prove IL4. Let's prove that if f and g are integrable, then the integral of the sum is the sum of integrals. All right, so let's try it. I'll do sort of a teal here, proof. Since f and g are integrable, we know that the limit, or excuse me, I could say this. The integral from a to b of f of x dx is equal to the limit as n approaches infinity of b minus a over n times the sum as k ranges from 1 to n of f of a plus, or I'll do it like this. I'll make it a little bit easier to look at. T sub k, where that tag, of course, is chosen to be the right endpoint. So that would be a plus k times this interval length, b minus a over n. Okay. And we could even choose, we can even rewrite this object as delta sub. Well, no, I think I'm going to leave it like that. I think this is good. And we also know the same corresponding sentence for g. So a to b of g of x dx. Since that is integrable, we know we can write this as the limit as n approaches infinity of b minus a over n times the sum as k ranges from 1 to n of g of t sub k. And again, where t sub k is defined as that way in both of these cases. Well, then what would this object be? What is this object? The integral from a to b of f of x plus g of x dx. That is, by definition, the limit as n approaches infinity of f of t sub k plus g of t sub k. Okay? But this is the same thing as the limit as n approaches infinity of b minus a over n. And this is a finite sum. So all I'm about to do is use the associative property and the commutative property. This is equal to, so what we have is the sum as k ranges from 1 to n of f of t sub k plus the sum as k ranges from 1 to n of g of t sub k. So I'll say because commutative property and associative property, field axioms. But this is the same thing, again, because of the distributive property. The limit as n approaches infinity of b minus a over n times the sum as k ranges from 1 to n of f of t sub k plus b minus a over n times the sum as k ranges from 1 to n of g of t sub k. That is because of the distributive property. But this is the same thing as the limit as n approaches infinity of b minus a over n times the sum as k ranges from 1 to n of f of t sub k plus the limit as n approaches infinity of b minus a over n times the sum as k ranges from 1 to n of g of t sub k. And of course, by definition, look at what we have. This object right here is the same as this object, which is by definition this thing. This object right here is the same as this object, and that's by definition this thing. And that is what we wanted to prove. This is equal to the integral from a to b of f of x dx plus the integral from a to b of g of x dx.